All right, by now we've talked about position time graphs and what type of information we can get from those. Like the slope is velocity on a position time graph. We can see the initial position that y-intercept represents the initial position, and we can compare the movement of different objects. Our second way of looking at motion is going to be through these things called motion maps. So what is a motion map? A motion map is a one-dimensional representation of an object's motion. Just another way for us to look at it. There are a few rules and regulations, and what I mean by rules and regulations are kind of the systematic way that, or the systematic way that we approach this. So, each dot will represent the object's position. So, kind of highlighting what things are. The dots are going to represent the position. Arrows are drawn from the dots to represent velocity. So again, the arrow portion is going to represent velocity. Remember, this is showing magnitude and direction, so I can have an arrow going to the right, an arrow going to the left, a small arrow, or a large arrow. So the magnitude is the size of the arrow and the direction is whichever way the arrow is pointing. The first dot for us will represent the position at a time of 0 seconds. So kind of just our starting motion. It's synonymous to the y-intercept on a position time graph. But we want to really make sure we know what we're talking about when we're looking at these. Each successive dot, so if we look at, I have a dot here with an arrow and then another dot with an arrow, will represent the passing of one time unit. Generally for us, again, if this was like time equals 0, from 0, this is 1 second has passed. We'll generally keep a time differentiation of 1 second in between the dots, but they could be defined as something else. So it could be 5 seconds between every dot, or it could be 10 seconds that has passed between every dot. That's usually stated, and if it's not stated, it would be assumed to be 1. We get to some situations where perhaps the object is standing still. And on a position time graph, that would have been represented by a horizontal line. But for this, if I'm trying to show you dots and the object's not moving, the dots just keep overlapping. If you were to guess how many times or for what amount of time I had made those dots, you wouldn't be able to tell because they're directly on top of each other. So because we can't just say how dark the dot is or how much ink was left there, we are going to stack dots. So something like this. So if it's at that position and stopped, we just keep moving up, up, and up for each successive second. So this would have represented 1, 2, 3 seconds of standing still. The parentheses you don't need to add. To show an object standing still. And if you're there, you can go up with the dots, you can go down. There's really no rhyme or reason to it, but we just don't want them overlapping each other. Again, same position, just showing that time has passed. All right, and this is kind of a quantifying one, what we'll look at later. For each dot, look ahead to the object's motion. We'll talk about that one in a second. What must you label for the motion map? You must label the time scale. So delta t equals what? If it usually equals 1 second, then that's fine. The other one is where time is equal to 0. So label where time is equal to 0. And then the other thing that's usually labeled for you is the axis, and that's the x-axis. It's position and with units. So meters are the ones we have below. It could still be position in centimeters, but it's up to you. All right, let's take a look at the first example. It says an object starts at the origin. It moves in the positive direction with a constant speed of 5 meters per second for a total of 6 seconds. The axis is drawn for us. We see that there's a position in meters and meters. We see that the origin is labeled as 0, and it says the object starts at the origin. So I'm going to start with my dot at the origin. And then the next piece of information that's given is it's moving in the positive direction. So any of my arrows that I'm drawing must be to the right, with a constant speed of 5 meters per second. This is a qualitative motion map because I don't have any numbers, so whatever I decide the size of the arrow to be, that will represent 5 meters per second in the size or the magnitude. The direction again is to the right, so that's taking care of the positive direction. So time equals 0 seconds at this dot. And then we would have to continue on. It says a constant speed of 5 meters per second for a total of 6 seconds. So I draw my arrows the same size to show that my speed is constant. And we'll count out. We have 1, 2, 3, 4, 5. And then we would have to go for another 6. Remember, this is time equals 0. So 1, 2, 3, 4, 5, 6 seconds. And because if I were to leave that as just a dot with no arrow, you would assume it was stopped. We tend to follow this last rule here that says for each dot, look ahead to the object's motion. So we're just going to assume it's still doing what it was doing after that last second. It's not the biggest deal to talk about it, but I think it makes more sense to see it with an arrow as opposed to without, because we again see that it's stopped. If you're worried that you haven't drawn your arrows the same size, and they really should be the same size, you can draw congruency marks on them, those little ticks, so just make sure they all match. If you have 2 different sizes, you can use 2 different congruency marks. And again, to count this out, if this is time equals 0, this happens for 1, 2, 3, 4, 5, 6 seconds. So that showed us 6 seconds. The blue portion you don't need to include, just kind of to help you count. Each arrow stands for 5 meters per second, so you can kind of label your speeds. Again, you don't have to, but just so you know what you're talking about. Let's take a look at 2 more. So we'll go down to number 2. An object starts at the origin. It moves with a constant velocity of negative 8.4 meters per second for a total of 3 seconds. I guess we did 6 before. So again, we're starting at the origin, but this time we're moving in the negative direction because the velocity is negative. So we're now drawing ours to the left. This arrow size is going to represent 8.4, and it's traveling for a total of 3 seconds. I have 0, time equals 0 here, so 1, 2, and I need 1 more to represent that 3 seconds there. I want to show that these are a different size than the one above, but all the same to each other. You can draw 2 tick marks or congruency marks on those. And for the last one that I want to go over, just so we see an example of stopping, we'll go straight to number 4. An object starts at the origin. It moves with a constant velocity of 2 meters per second for a total of 3 seconds, and then stops for 2 seconds. So we have this second part of the motion. Starts at the origin, so we got that. A velocity of positive 2 meters per second, so we are traveling to the right for 3 seconds. So this is where it gets kind of tricky. If this is time equals 0, this is 1, 2, and then 3 seconds. And where we were used to drawing that extra arrow, we know what happens right after 3 seconds. Right after 3 seconds, the object stops for 2 seconds. So we do want this to not have an arrow. We want it to represent the object stopping. But the object is stopped for 2 seconds. So we need to draw another dot that would show 1 second of stopping and one more. So if we were to count this out again, just to double check we did our times right, 1, 2, 3 of motion, and then 1, 2 of stopped. All right, that's it. Finish up the rest for homework, and I will see you later.